So it's my pleasure to, today the talk is about a very exciting topic, AI and climate change. I was telling Professor Gentine that, that we heard the news that a very famous venture capitalist in California, John Doerr, decided to give $1.1 billion to Stanford to open a climate school, right? But Stanford was not the first university to do that, right? Columbia has also has started also a climate school last year. So it's a very big deal. And as you know, also the IPCC released a very concerning report. I mean, they've been releasing these kind of reports for the past few years already. But the last one was very alarming, and we all know that we need to do something. I talked to many researchers about Pierre, because I told them, I've managed to invite Professor Gentine to come to the talk, and everybody knows him. It's kind of amazing that in the community of AI and climate change, like everybody knows Pierre Gentine, so we're very fortunate to have him. So let me introduce him to you. So he's a professor at the Department of Earth and Environmental Engineering and at the Department of Earth and Environmental Sciences at Columbia University. He's also the director of the National Science Foundation Science and Technology Center, Learning the Earth with Artificial Intelligence and Physics. And he's also director of the graduate program in Earth Environmental Engineering. So he investigates multi-scale nature of the continental hydrologic and carbon cycle, but he'll tell us about during his presentation. Professor Gentine is originally from France. He graduated from one of the top universities in France called Super-Héros, and he got his PhD from MIT, and he joined Columbia after that. So now the floor is yours. Okay, Pierre?
Yeah, thanks so much. Yeah, and thanks for the introduction. Yeah, so it's a pleasure today to talk about, I'll be mostly talking a little about our center and what we intend to do. And it's not going to be extremely science-based, but I'll try to give a view as to why we believe AI could be very powerful if we want to start thinking about climate change and how to adapt to climate change. And so the name of our center is called LEAP, and that stands for Learning the Earth with Artificial Intelligence and Physics. So yeah, and that's a joint effort I should mention between Columbia, who's the lead, NYU, UC Irvine, Teachers College, University of Minnesota, and the very important Climate Lab, NCAR, and we also have like NASA as a collaborator, I should mention as well. Okay, so I'll try to give a little bit of background as to, because sometimes there's a bit of confusion I always find when we start thinking about climate change. So really starting to get to the basics and to really start understanding climate change. And to understand climate change, what we need to first understand are greenhouse gas effects. And sorry, if you could mute yourself, I think maybe.
Yeah, Angela, yeah, you could mute yourself.
Yeah, I'm so happy you're like.
Thank you. Thanks so much. And so first understanding the greenhouse gas effect and why and how the planet is warming. And then talking about emissions and carbon dioxide, so why is the planet warming and what are the implications of that? And then we'll talk about climate mitigation and climate adaptation. And those are two key elements of our strategy to tackle climate change. And we'll try to see how we can go about it. And then I try to explain and try to justify why we believe that artificial intelligence and machine learning can be a very useful tool when we start thinking about climate adaptation in particular. And there might be some really exciting things on climate mitigation, but I leave that for to someone else, for sure. Okay, so first of all, what's the greenhouse gas effect? So basically, as my son would put it, a little bit of greenhouse gas is actually a good thing, so it makes our planet warm and kind of comfy, so that's great. But too much of that is actually not that great. So as we start increasing the greenhouse gas concentration, what will happen is that we start trapping more and more of the radiation. And then basically we are starting to warm the surface and what we call the lower atmosphere. And so as we keep increasing the greenhouse gas concentration, you can think of that we're really like trapping a lot of the radiation, and therefore we are actually starting to keep warming up the planet. So really, as concentration rises, the planet basically warms, especially in the lower layer of the atmosphere and at the surface, which is where we live and what we feel on an everyday basis. And of course, I mean, that sounds like those are like basics, but the human emissions are the largest share of the greenhouse gas emissions. So, and a lot of that is coming from the energy sector. If you wanted to actually start thinking about, you know, the share of the emissions, transportation being a big chunk here at the top, electricity and heat, we oftentimes forget about that, but heating your home or cooling your home, you know, in the summer, those are like big emitters. Industries, of course, as you would expect, and fuel combustion, you know, and a lot of that will actually lead to like some carbon dioxide, so CO2 emissions, you know, which is basically the largest share of the greenhouse gas emissions. But you also have some other greenhouse gases. So we have methane, which is actually, and that's been discussed a lot at the last COP meeting. Methane is actually a very potent greenhouse gas. It actually naturally decay in the atmosphere. So there's also like that's an advantage if you think compared to carbon dioxide, which stays in the atmosphere. And then you have nitrous oxide also, that's especially coming from agriculture and livestock as well. And we have things that have been happening just also before the pre-industrial revolution, such as land use change, right? So and the fact that we were already emitting before we were actually we were having an industrial revolution. Okay, so that's been happening for a while. And I should say that all of them are actually contributing to this greenhouse gas effect that's actually warming the planet. Now, to give you an example, because I always find that useful to start thinking about, you know, what's the difference between the emissions, so the flux, you know, that's how much we put up in the atmosphere, and what's the difference between that, the concentration, so what stays there, and the warming, you know. And I think I always think of that like you can think of that like as a bathtub, right? A bathtub where the emission will be like the flux, so that's the amount of water that's actually getting into the bathtub. The concentration is by how much water we're actually filling the bathtub, right? And so there's always a difference, right? So the flux is basically by how much you're actually filling it up. And then what you would want to know is the concentration is basically the amount, and that's really what's going to contribute to the warming, right? So there's a little bit of a difference between the two, and really it's the cumulative of the emissions that's going to be leading to this like pool in the bathtub, or the bulk of the concentration. So if you start, say, on the left-hand side, just to give you an example. So if we were to think about, say, transportation, for instance, imagine we keep on increasing the emissions. So imagine the number of cars, or we don't make much progress in terms of reducing the emissions of a particular car, and we keep increasing the number of cars. So the emissions will continue to rise, right? That's basically the red arrow that we have here. And as a result, what will happen is, of course, the concentrations will keep on increasing, right? And of course, the warming will keep on increasing, which is the red arrow that we have here, right? So that keeps, that's basically what you would expect. The other thing that's sometimes where there's a little bit of confusion, but if the emissions were fixed, right? We are just not, for instance, you have more cars, but the cars become more efficient, you know? So on average, if we average that over the entire globe, we have the same amount of emission, we remain flat, right? And you feel we're making progress, right? Because, okay, the cars are becoming more efficient, but you're emitting, so you keep, again, if you think about the bathtub, you keep adding water into that, so the level will actually continue to rise, right? So the CO2 concentration will continue to rise, and therefore the warming will continue, right? It's not as fast as what we had before, but it will still continue to rise, right? So it means that to make progress, being flat is not sufficient, right? And so what it means is you need to get to the blue area here, where we need to have a falling rate of the emissions, right? So we need to reduce the emissions as a whole, globally in that case. And even then, you know, even if you were to still emit, which we will be doing for a very long time, you will still be continuing to warm up the planet. Maybe not as fast as this linear behavior that we had here, but we will still continue to rise until we reach a level where we have basically zero emission, right? And that's again the analogy of the bathtub, where you stop basically adding water into the bathtub, and therefore the concentration remains flat, and therefore there's no change after a little bit of time. There will be no change in the warming, right? So that's really what we would need if we really wanted to stop the warming, right? We need to basically reduce the emissions to zero, which is a huge challenge. You know, it's a technological challenge, right? I mean, you need to have all renewable fuels, or you need to use all renewables. So that's going to be a major challenge. And ideally, so that would be the best scenario, which is on the right-hand side here. So that's the dashed red line here. We'll be able to actually remove carbon from the atmosphere. We'll be able to do carbon capture and carbon sequestration, right? So there's quite a few people, including at Columbia, but not only, like across the globe, trying to look at mechanisms by which we could extract carbon dioxide from the air, remove that, and sequester somewhere, typically in geological form or into the ocean. And then only in that case, we'll be able to actually reduce the warming, right? Because we will be taking off, again, if you think about the bathtub, we'll be taking off some of the water level, right? And therefore, the warming will start removing. But that's really a climatic, we call it climate tech. That's a climate technological breakthrough, basically, that we need to do it at scale, because we can do it maybe as a prototype, but we are unable to do it at scale right now. Okay, but just to give you a sense of that. And methane, which is here, CH4, the main difference that we have is it's a naturally decaying gas, and therefore that's going to be slightly different in the sense that even if we were to keep the emissions fixed, so the warming will actually remain flat because there's the natural decay in the atmosphere. Okay, and so if we were just to reduce that, just to reduce the emissions, we'll be able to actually reduce the warming by itself because there's this natural decaying process in the atmosphere. So that will be less of a breakthrough in that case. So just reducing the emissions will actually play in our favor in that case. We don't need to get to negative values. Okay, so that's kind of the baseline for what climate change is about. So, and then we have kind of two sides of the story about climate change and how as humans we are going to adjust to that or fight climate change to some extent. On the left-hand side is climate mitigation, which is preventing and reducing the change. So as I showed you before, so for instance, some breakthrough in technology to remove carbon from the atmosphere, reducing the emissions as well. So everything we can do to actually mitigate climate change. And then on the right-hand side, we have what we call climate adaptation. And basically what this is saying is that climate change is happening and it can be stopped. So how do we adapt to that? Or maybe it can be stopped, but not right now. So how can we adapt to that? And you can think about adaptation in terms of infrastructure or many other components, you know, so things are happening and how do we adapt as a society or as humans? If we think about climate adaptation, so basically what it means, again, climate change is happening right now. And that's basically what you're seeing on the left-hand side here, where the global temperature has been rising, and we know that that's been observed, or it's being observed using satellite data, for instance, and weather data. And that's not just a global thing, but it's also a regional thing, right? So on the left-hand side is the global temperature. So it's the aggregate of temperature as it's been warming throughout the globe. So like roughly 1 degree Celsius. But if you look, there's substantial heterogeneity, you know. And I think one thing that should stand out is that it's very clear that the continents are warming way more than the ocean, right? And you can see that there's a very strong gradient also towards the poles, where there's actually a lot more warming, this what we call polar amplification. There's a lot more warming, and you could get into the weeds, like the permafrost could be warming quicker. So there's quite a few implications of that. But the main point being that there's a lot more warming over the continents as opposed to the ocean. And a lot of that is due to the inertia, because water has a lot of inertia. So the continents are basically warming faster, and that's unfortunately where we live. So there's a little bit of an abstraction between the 1 degree of warming, or what we call the Paris Agreement for 1.5 or 2 degree of warming compared to pre-industrial, And then what we would expect over the continents, which is roughly double, I mean, depending on the place, but roughly double of that, so double that. So that's actually important to keep in mind. And it's not just kind of the average temperature that's been changing, but a lot of the extremes as well, right? So if we think about, say, heat waves and the heat wave frequency, so that's the number of heat waves per year over the US, and that's been basically increasing with climate change, and we know that's going to be dramatically increased in terms of the amplitude, but also in terms of the frequency of those heat wave events. And that's exactly where adaptation comes in. How do we adapt to that as a society, to those extreme events, and not just to heat waves, but also to flooding, to droughts, or wildfires that has been pretty big also in the news recently. So all of those events are very strongly attributable to climate change and their increase in particular. And kind of related to that is the fact that all of those extreme events, so drought, flooding, freeze, severe storm, tropical cyclones and hurricanes, wildfires and storms, have been increasing in frequency, and as a result, also in terms of cost, a cost for society. So that's the number of billion-dollar disaster per event type and per year. And you can see there's been a dramatic increase in terms of the impact on society. And that's basically where the cost comes in. That's something we need to address kind of hands-on. So what we've learned so far is that really that we know that climate change is happening. We kind of know why. I mean, because of anthropogenic emissions. And we talked a little bit about the greenhouse gas effect and carbon dioxide in particular. And what's very clear is that there's very strong impact on climate and on extremes. And so the question is, what do we do about it? And what's going to happen? And so to adapt, really, what we need is, what we are trying to do is, you can think of that. I mean, for instance, I always take the analogy of finance. You would want to kind of know what's going to happen next, right? I mean, and so we are pretty good about thinking about finance, so like, for instance, stock market and things, there's quite a bit of variability, which is pretty natural in the climate system. There's natural variability, very similar to what we call volatility in the financial market. But we want to actually get a good sense as to what is going to be our best bet, for the prediction, so it's quite similar. And really what we want to do is we want to basically try and get our best estimate of our, what we call climate projection, so the prediction in the future. And what we mean there is that we want to try as much as possible to reduce the uncertainties, right? So we want to have as much confidence as we can in what we call climate projection. So again, those projections a few decades ahead of time. And really what we are trying to do in the center is trying to basically use what we call a climate model that's being used to represent climate change, and also trying to use the data so we can best estimate that. And we are trying to do that roughly at a time scale of 10 to 40 years. And we believe that's going to be important because that's where a lot of the investment, and that can be in terms of public and private investment, urban planning, and also in terms of also potentially behavioral change, that's really where a lot of things are going to happen. So that's really kind of the target, 10 to 40 years. And you can ask, why don't you go to further down the road, like to 100 years? But 100 years becomes very tricky because then you need to factor in a lot of like socioeconomic behavior. Will there be more growth? Will there be a technological breakthrough to actually remove carbon dioxide from the air, et cetera, et cetera? So a lot of things that are very unknown, which we call the scenarios. And so we kind of leave that aside and just say, okay, let's try to get more confidence between 10 to 40 years. And we know that a lot of the uncertainties are coming from physical processes. And we hope that the data we can acquire, such as from satellite data, can actually help us do a better job, if that makes sense. So why, so I mentioned before that, so the projections that we have are uncertain, but why are they uncertain? So if you look, so those are examples here. If we look again at this global temperature, so we take the planet and we look at the average surface air temperature, And that's a new generation of climate models and trying to actually predict what's going to, or what we call project, but let's call that a prediction by 2060, you know. And what we can see here is that there's a lot of spread. So the envelope that you're seeing here is the spread across the different models. So you have many models across the different, say, countries or different research groups or centers across the globe. And everyone will actually report their best estimate of their projection of the future. And the issue is that this range is actually pretty dramatic. You know, when you look at the model spread here, it's almost as large as really like the amplitude we're looking for. Like the Paris Agreement is, say, 2 degrees of warming, and the spread here is actually more than 2 degrees. So it becomes really difficult. It's like signal to noise ratio, right? It's very difficult to disentangle what's going to be the signal compared to kind of the noise, and to actually make a good educated guess as for our projection. And the socioeconomic scenarios I mentioned before, the different lines and the different colors you can see here, where we actually prescribe different scenarios for the emissions, you know, or the concentrations, where we say, okay, here is an optimistic scenario, here is a more pessimistic scenario. So at the very top where it's warming more is a more pessimistic scenario, and at the bottom is a slightly more optimistic scenario. So that's why we still want to get within that range of 2060, where a lot of the uncertainty is not dominated by those scenarios, so those different lines or those different colors, but more by, again, the physical processes. And really the issue is that those, or that spread or those uncertainties really do not really translate into actionable adaptation, because ideally you would want to say, okay, sea level rise in New York City is going to be between this amount and that amount, and you want to be relatively narrow, right? So you can plan, for instance, some infrastructure, you know, to actually reduce inundations or something like that. But you need to be relatively narrow, right? Otherwise, there's a cost to that. Like if you're saying that there's a huge range, I mean, you will need to actually invest either for the worst case scenario, but that's going to be extremely costly, or you can do something less aggressive, but then you're going to be flooded very frequently if that were to be incorrect, right? So that has a lot of value, getting that information correct, right? Like making sure that you can actually reduce those errors and being more accurate in terms of the prediction in the future. And a lot of those uncertainties actually here, you can relate to what we call physical processes, such as clouds. I mean, it sounds really obvious, but actually those clouds are actually very important. And the trouble is that they are super tiny, right? I mean, so that's an example here taken from the International Space Shuttle. But you know, like many of the clouds, I mean, you can see them when you take a plane, and many of them are really small, but they are very bright, right? So they reflect a lot of energy back to space, and therefore they modulate the response to global warming, right? So, and one way to think about that is if you have a lot of clouds and they are very bright, they would actually reflect a lot of energy back to space. So they would actually buy us time, right? They would actually cool up the planet to a large extent. And if now you have a model where clouds are represented slightly differently, where the clouds are darker or you have fewer clouds, then in that case, they will actually trap a little bit more energy, right? So what it means is that things as simple as clouds, you know, will have a huge impact on the response of the planet to greenhouse gases, you know. And so it's a modulation of global warming, which really explains a lot of the spread we see across different models, because every model has a different way of dealing with clouds or dealing with some of those physical processes. So at the end of the day, those small physical processes are really critical to explain the kind of the fate of the planet, as crazy as it sounds. But that's really the end of, that's kind of the bottleneck here. And so really what we are trying to do as part of the center is try and refine the representation of those clouds, because in the climate models that we are typically dealing with a very coarse resolution of, say, 100 kilometers. And we need to represent those clouds. We cannot directly represent them as accurately as what I have here, but you could think of that, it's like the old computer games, you know, where it's very pixelated, right? And we need to have like the typical behavior or the typical response of those clouds. So we need to have like some sort of statistical representation of the effect of those clouds. And that's really what we are trying to do. And that's what we are trying to do now with machine learning, as opposed to some sort of empirical representation that was leading to a lot of that spread. So we are trying to be more objective in a sense using machine learning. And so we're trying to use a lot of the data that we have. So, and we are trying to increase the data volume, but also the diversity of data that we are using. So having a lot more fleets of satellite data, but also using what we call high fidelity simulations, where we can potentially represent those clouds relatively well, or like some other processes such as ocean eddy mixing or things along those lines. And that's really what we're trying to do, is harvesting the data that we have and then plugging that into those climate models to actually do a better job. And then the idea is to actually use this data as a way to actually provide those more accurate projections. And why is that useful? And we believe it's useful to have reliable projections for many different components, starting, for instance, from urban plannings to like law and legal regulations, you know, because a lot of things will want to actually be regulated, and we will want to know what is actually attributable, as we call it, to climate change. So how much, for instance, if you think of a flooding, you could say how much of that can be explained by climate change or not, you know. Think about wildfire, how much of that is land management or forest management as opposed to climate change, for instance. Agriculture and food, you know, you would want to look at yield, for instance. How much is the yield going to change with the warming climate? You know, is that going to have an impact on food security at the global scale? So those are key questions we need to face. We can start thinking also about vulnerable communities, because we know there's quite a bit of gradient in terms of the impact of climate change, especially one example is heat wave, where if you have an AC system, you'll be fine, you know, but if you don't, so say, for instance, maybe in the Bronx, you might not have access to that or you cannot really pay the bill. So that could be an issue as well. There's been a lot of work as well on global conflicts and how they are related to climate change. So for instance, there's been some very interesting work on the Arabic Spring and how, of course, there was a lot of background and political background in there, but how potentially some issues with harvesting for a few years actually led to that, and droughts. Restoration, social services, migrations as a result of, especially of those conflicts and droughts, especially in the Sahel, where people are expecting major migrations as a result of climate change as well. So a lot of things where reliable projection could really help for the planning or to actually be ready, you know. And I always think of that, you know, you can think of kind of the same as for COVID, you know, this projection is very useful to be ready as a society, you know, when we can have a good estimate, okay, that number of cases is actually increasing, that's the type of measures you need to take. So planning is actually very useful to be safe in a sense. So kind of the idea for the center is really to use the data and try to use and define a new field, which is at the interface between climate science and data science. And we call that climate data science, to revolutionize climate projection. So again, to actually embed data science and machine learning at the core of climate projections. And our mission statement, our mission is to have a leap forward in the reliability, utility, and reach of climate projections through that synergistic innovations between data science and climate science. And I'll explain what I mean by those terms. So by reliability, what we really mean is that we want to kind of, for the first time, around one of the first times, we want to actually really base our projections or prediction again in the future through a data-driven type of approach, right? We want to harvest a lot of the data that is existing from satellite observations, from high fidelity simulations, and use that to increase that reliability to make sure that our projections are more accurate, basically. We want to increase the utility, and kind of the idea here is to have a platform where you can really have like this knowledge transfer to society, where people can actually use the data, extract the data on the fly of climate projections so they can use them for their needs. It could be for the public sector or the private sector, or you could be an individual. And for instance, you want to look at your house and you want to know, okay, what's going to be flooding like in my particular location. And we want to increase the reach through different mechanisms. So of course, a pipeline where we want to have more diverse scientists, especially because our field of the geosciences is quite diverse. And also by this platform where we want to use cloud computing as a way to actually basically perform all of that data computing on the cloud, and then you could directly use that on your laptop. So you would not need a major infrastructure. You could just use the existing infrastructure, so you could directly use that information without actually having to carry all of the weight of all of that data and all of the computing resources. And really, we believe that the novelty of this center, which we call LEAP, is to be really leveraging, but also advancing data science across the entire climate modeling pipeline. And that's kind of the idea, and the goal is to get from this pixelated view of the world to a much more, much higher fidelity view of the world that will be much more realistic, and where we believe will be having an edge in terms of better projecting the future. And that's kind of how we see that. So having this convergence between climate and data science across the different components of the Earth, from land, atmosphere, ocean, and cryosphere, but also really embedding data and knowledge as well. So we really see that together. So physical knowledge and data and machine learning. Using that to develop the next generation of climate projections that are more accurate, and then using that and transferring that, but also creating a platform for bidirectional knowledge transfer through this cloud computing platform that we call Leap and Geo. That's a data infrastructure on the cloud where you can really use the data for the research, but also for the educational or for the knowledge transfer component. And we'll do that as well through a broadening participation to make sure we can actually reach everyone, because everyone is going to be impacted by climate change and everyone will have to fight climate change. So it's very crucial that everyone gets involved. On the data infrastructure, so I mentioned that, so that's very much led by my colleague Ryan Abadnati and colleagues as well. And so the idea is to actually go beyond this typical download model where you have like large data sets and you analyze them and you do your business on your laptop. But a lot of that now is pretty much impossible because we are dealing with petabytes of data. And that's really this idea of data approximate computing, where a lot of the data is on the cloud, or most of the data is on the cloud, and you're doing the computing close to the cloud, right? So on the cloud directly, so close to the data. So there's no downloading bottleneck. And we can actually also very much share notebooks or codes, you know, so that's a much more open source type of perspective as well. So which is much better for science as a whole, so we can really evolve as a community. And then we can use that also for this knowledge transfer, because we can use the same data, and that's very transparent. You know, there's no issue of transparency, and we can actually use that on even a simple laptop here, wherever you are. You know, you don't need much computing power. And then we can actually use these data from very raw data sets, if you're very familiar with the data set, to more aggregated data sets, all the way to actually very specialized data that we can define based on metrics that people will need. And really what we are trying to do is having different types of segments in terms of the corporate and public audience as well, from people that are really into the technical details of how to use the data sets, all the way to people that will need more aggregated metrics of climate change dedicated to their needs. So we want to have kind of segments of those things so that we could actually reach a broader community, and so that people can better use climate information, basically, and all through the data platform and data portal. And then what we want to do is we want also not just to use off-the-shelf type machine learning, but also developing new type of machine learning. And what we mean by that is actually embedding physical laws here within some machine learning component, but also including causal behavior and causal knowledge, right? So that you can actually be a bit more realistic. It's not just building up correlation in data sets, you know, and getting the right answer for the wrong reasons, but trying to really look at cause and effect, you know, like how can we actually get those things? And the idea is to have then in the end an algorithm that will actually better extrapolate, better generalize to conditions it has never seen. And climate change is all about generalizing to conditions we've never seen in the past. And also as a way to better interpret the data. So what we call trustworthiness in AI, you know, and also this interpretability in AI, which is actually very important. And finally, what we want is using those new algorithms. We want to combine observations, as I mentioned before, from satellites that you have here, along with high fidelity models. So you could actually have very detailed simulations, such as clouds here. I'm showing here from what we call large simulation, where you can resolve the details of those clouds. And then combining that together as a way to better represent those physical processes in climate models and getting into that next generation of modeling, especially with NCAR, our partner who's developing the community Earth system model. So that's an open source code. And to get to these those more accurate projections that people will need. And we believe that should work. I mean, we have at least some proofs of concept. So that's an example we did with the colleagues at UC Irvine in particular, where we have these high resolution simulations here on the left-hand side. So that's, you can think of that, that's moisture. On the right is like heating. And we were trying to replicate that with the neural network. And you can see that there's very good accuracy in terms of replicating that with a statistical model, so with the neural network. So we believe that there's really good potential for that to work. You know, we can use those high fidelity, high resolution simulations, and we can actually replicate them relatively well using those neural networks. So we believe that, I mean, there's of course a lot of work to be done, but at least we know that there's some proof of concept that seems to work.
Well, what is the time horizon here? Is it like a day, a month, a year? Like in,
so those are several days. So every time
several
you
days.
can,
Okay.
yes, several days. Every time you see, oh, sorry. Oh, I don't know what I did. Ah, sorry, let me reshare that. Yeah, every time you see, that's a diurnal cycle. Like every time you see the heating going on, like that's one day, another day, another day, etc.
Oh, okay, okay, thanks.
And finally, what we are trying to do as part of the center is really creating that convergence between climate and data science. And what we believe is that by doing this research immersive educational component, then we can actually start building this discipline because historically there's been different jargons. You know, people in the machine learning or data science community use different wording as opposed to the climate scientists. So it's been difficult to actually generate collaboration, and we want to actually put people in the same room and then starting to actually start doing research together. And so we are really trying to do that from the bottom up, especially by using research integrated curricula and developing new classes as well, looking at projects specifically for climate change. And kind of what we believe should be the legacy from 5 to 10 years from now. So the center life cycle should be 5 years, potentially a renewal for another 5 years. We hope to have improved climate projections, again, with reduced uncertainty, so we can actually be better for climate adaptation, and so can have better information in terms of climate forecast, if you will, or prediction in the future. We want to train a new generation of scientists, which is critically needed. So there's a lot of demand now in terms of trying to get people that are well-versed in terms of understanding climate change, but also knowing how to use data at the same time. And we are just missing those people altogether, like people that know how to use machine learning and for climate adaptation or climate mitigation or some other components. We want to be much more diverse. Again, there's historically a big bottleneck in terms of the diversity component, especially in the geoscience. And we want to be a representative of the US population after 10 years. And we really want to establish a community and dialogue with the basically heterogeneous stakeholders for actionable climate adaptation. And again, going across different segments from very detailed data sets all the way to more like coarser and broader metrics that people will use and they will believe are important to adapt to climate change. So with that, I would be happy to take any questions. Thanks for your time.
Okay, thank you. Thank you.